Olaf and Sandro this morning talked about excuses, and I think our ambition should be to make away with the need for excuses. Our ambition should be to provide a sufficient user experience to customers, users that are mobile. And I want to talk to you about a little bit on what we're doing to advance that. So I'm talking, of course, about 5G NTN for automotive, but complementing what Uwe and Olaf said, and then the two projects that are actually at the core of what we have been doing in this respect, nationally I should say, 5G Autosat and 5G Autosat KI, and then a slight deviation towards the AI applications and intelligent satellite payloads. And I hope you then have something to take away from here. So 2022 was a very good year for 5G NTN for satellites because release 17 was finalized, and with it, satellite access for 5G systems was introduced. It became part of the 5G system requirements. It was integrated into system architecture and radio access network specifications. There were even a few dedicated radio access network NTN specifications. And beginning with this year, we're now working on release 18. Work items for NTN new radio, but also narrowband IoT. And as Uwe already pointed out, for release 19, we're expecting some enhancements. There are a lot of preparations right now on the 5G AA side, but also on the satellite community side to define what goes into release 19 for the standardization. And that could be regenerative payloads and things like that. So we have a lot to look forward to. Now, the impact of 5G NTN specification, really 5G satellites becoming part of the specification, is immense. We're for the first time talking about direct satellite radio access that is standardized. And this standardization enhances reliability and stability for the users, for the vertical markets, and for the manufacturers of the equipment, because you can now rely to be interoperable and you can rely on being compatible to other units. And this also paves the way for TN NTN integration, which is not perfect right now, but we're on the way to that. It also means increased competition and innovation. And we've seen this last year, that the chipsets for release 17 were on the market quicker than we had actually expected. We were talking about 1.5 years. MediaTek announced its commercially ready NTN NB-IoT chipsets 8 months after the freeze of release 17. So this is really excellent. And yeah, it paves the way for really implementing NTN relatively quickly. Of course, there are still a few obstacles that I'm going to talk about later. But with that, with the NTN specification, satellites have the chance to become part of the global telecommunications ecosystem. And with that, analysts say, well, we expect that 65% of the satellite communication revenues will be 5G by 2030, or perhaps even 6G. So this means it's an important topic for us to also address. And of course, a lot will be carried by the direct handheld to satellite, but also by the mobility applications. So this is the slide that actually connects to what Uwe and Olaf have been saying, and this is the only slide. I won't even go into the use cases because Olaf mentioned them quite a bit, and we've done a lot on 5G AA to define them. Connectivity is an enabler for the car of the future. So a lot of connectivity platforms, mobility services, new ways of earning money for the automotive OEMs, strongly demanded. And we've seen Uwe's picture on the gaps in terrestrial network coverage. Mine here is a little bit closer to home. This is actually where our site is. It's the Lake of Constance. But even there's bad connectivity. Driving along from work to home, I get interruptions. So 5G satellite connectivity can serve as a complement, not substituting terrestrial coverage, but complementing terrestrial coverage. But as I said before, there are still some obstacles. And actually it was Olaf that pointed them out. Really the complete end-to-end design, the system design and the performance within such a beam. How do I handle the different number of users in there is not really completely solved, I would say. Second obstacle, of course, car integration of antennas and modems. Then something that's very important for us to provide for us on our task sheet, availability and the cost of satellite connections. So really having NTN satellites in orbit, which we don't have today, and bringing down the cost of having 5G NTN constellations. And then ultimately also the viable and validated business cases that come along with all that. Within the discussions that we had also with 5GA or within 5GA, which also Airbus is a member of, and this is basically thanks to Dominic, who's also here in the audience from our central research, who initiated that. And this really brought this topic very quickly forward. We've been talking about basically 2 phases or 2 to 3 phases. An initial capability that would serve narrowband use cases, and then later on an enhanced capability with wide and broadband use cases to really fully serve the users. So this obstacles is basically on our task sheet to solve, and we actually started quite a few years ago with the first project. Actually in 2019 we had started on a topic, I guess, a few years earlier, so 2016 to 17, but the really first project that we then started was called 5G Autosat, concept for a satellite-ready 5G telematics control unit for automotive. It ran for about 14 months, from August 19 to December 20, and the basic 4 topics that we addressed were, on the one hand side, the application, potential automotive use cases for 5G NTN. And this helped us also in the discussions then with the automotive industry, with the mobile network providers, with the telecommunications equipment providers, with 5GAA, to mature and align these use cases. Then a coarse architecture design on the system, a validation through a emulation of the air interface between the car and the satellite, and then a concept for a 5G NTN ready telematics control unit. And this we're currently continuing. We've started that about a year ago with the follow-on project 5G Autosat KI to move that to the next level, to actually be ready for this phase 2-3 with improved performance and improved capabilities. On the application side, we're talking about artificial intelligence. We are implementing a full end-to-end system level simulation to really understand how the switching between the different users and between the different beams can happen and should happen. The air interface simulation will be moved into a real-time lab demonstrator. And of course, we're working on the maturation of the telematics control unit. So let me go through these 4 areas from the bottom to the top in more detail. And I should say this is funded in part by the DLR agency, with support, of course, from the Ministry of Economics and Climate Protection. So the telematics control unit is the core of the vehicle. And someone asked the question before on how do we get ready? Well, we're trying to get ready for that with a automotive supplier. ZF is actually a close neighbor of us at the Lake of Constance. And they've started to work on this. They have this ProConnect product line for the telematics control unit. And this control unit is really the central unit in the vehicle to manage connectivity. On the one hand side, within the car, with the various buses, CAN bus, LIN bus, Ethernet USB, especially also the wireless. It contains the GNSS unit, 2G, 3G, 4G, LTE, 5G, Bluetooth, Wi-Fi, also the Sidelink or the V2X. And I have an example here. This is the latest one. This is the one that already contains 5G, but 5G terrestrial. This is the release 15 5G unit. And what you see here, you have the different connectors. And what we need in order to go to the next level is really the 5G NTN integration. It's just one additional antenna connection that would then connect to the car antenna. And you have here all the others for the GNSS antenna, for the Wi-Fi antenna, the power cord, and the buses. So this is really, the next step to use the Release 17 chipset, which then would be ready to do NTN, so just one chipset, and then connect the antenna that then would not need anything in the baseband, but just would need to do the down modulation and could do, send the signal then to this unit, which would mean you would save on chips, save costs. It also means that that would be basically compatible with different frequency ranges. So it would be compatible with the first phase 1 narrow band, L or S band release, and it could be later compatible with also Ka band. Frequency range 2, phase 2 and 3. So this is really what we are working on in 5G AutoSat Ki, and for this it is really good that the chipsets will be available much earlier than we thought they would. Of course, what also is needed, and this is something that we are not working on in 5G AutoSat Ki, is then also cost-efficient antenna concepts into the vehicles. But we know others are working on that. And perhaps for phase 1, we could even use existing car antennas in the S-band or in the L-band that are used for the GNSS functionalities. Second part is the real-time laboratory demonstrator. And that is mainly done at Fraunhofer. And it's there to perform really end-to-end tests of the air interface between the car, the simulated car, the user equipment, the NTN satellite, and then a gateway base station. Incorporating everything that is needed to do that and working based on the open air interface, implementing an RAN intelligent controller to really be very flexible and allow an optimization of the network. Which brings me to the next part, the system level simulation, which is done jointly between the University of Erlangen and Fraunhofer. It's an evaluation of the 5G NTN connectivity concepts in really realistic traffic scenarios. And I should put this up, that you see this is not just one single piece of software, but it's a relatively complex simulator, a complex set of simulators that work together in order to simulate the complex traffic scenario that we need. Because we need to know, if we have a large number of users in one satellite beam, and that could go up to 1,000, it could go up to 10,000. I mean, this is really realistic. How to mitigate between them, when to do handovers, who gets to go to which satellite, and so on. Who gets to switch to the terrestrial network. And this is the means to simulate that. Go one further, as to just show you a few more pictures from that and the features. So, of course, we need the satellite trajectories in there, multi-connectivity, configuration of the user equipment, the enhancements of the different layers, and then also implementation of the channel models, measurements of the KPIs. Of course, we have also OpenStreetMap, so that this is really, we can then include really real scenarios, and then we can simulate them to show what kind of user experience the individual users will really see. And hopefully be able, by mitigating between the different users, to really provide all of them with a sufficient, suitable, satisfactory user experience. And of course, for us, the important part is then to understand what do we need to do in the satellite to get this done. How does our payload have to look like in order to get this kind of performance? And this is the last part of what we're addressing. It's employing artificial intelligence and machine learning in the different parts of our architecture, in the network, for instance, specifically to do predictive quality of service and re-optimizing the end-to-end network, but also predicting handover and optimizing handover between the different satellites, between satellite and terrestrial, and between the different users, and determining which of the users should better stay on the terrestrial network because their outage will be minimal, and which of the ones should be moved to the non-terrestrial networks and perhaps even stay longer on the non-terrestrial network that is actually necessary in order to do some load balancing with other users in that area. This is also both done between Fraunhofer and IAS. On our side, what we're looking at is really edge computing services in the satellite, providing computing power in the satellite. The specific use case that we're looking at is anomaly detection for improved situational awareness, but we're also looking at other applications where we could actually provide edge computing services for any of the automotive applications that we could think of. And then in the vehicle, there would be, I would say, just enough computing power to support new services in the vehicle that we are offering, but perhaps also outsourcing some of the computing power to the satellite or perhaps even the core network in order to be as efficient as possible. And this is something, this interplay is also something that we are looking at in 5G Autosat KI project, where we're about approaching the midterm time. So one of the preconditions for that is, of course, to have the satellite be able to perform all that. And putting sufficient computing resources into the satellite is a challenge. And this is what we're working on heavily. We're using the latest version of field programmable gate arrays, FPGAs, that offer really a combination of computing engines, so a central CPU, the really hard, the programmable array, and then intelligent engines. So this is the Xilinx Versal that we're momentarily looking at. That's, we would say, the most advanced chip that's on the market, or platform actually, the computing platform that's on the market, and that would be ready to go into the satellite and reporting a number of applications there. So we would actually port a G-Node B into the Versal to be able to have a G-Node B in the satellite, a base station in the satellite, which would be something that will be specified in release 19. But we would also be able to do really computing services. This goes hand in hand with a project that we are just about to start that is called, from the ESA ITT, was repurposable 5G payload, which means we are going from a pure communication application into really a server in space that could serve 5G applications as well as Earth observation applications. This goes along the lines of convergence of space functions. Right now we have navigation, communication, and Earth observation. We will move all those together in the future. They will go hand in hand, which will also bring the costs down. And then we will be able to provide much better service. And another topic that is growing very rapidly, quite interesting, and it's also a new work item in the 5GAA, this is this integrated sensing and communication. Now, doing that from space will be completely different from what we're doing on Earth, where we use perhaps the radar distance signals for also communication. From space, it might be much more the other way around. We're using the communication signals also for additional sensing. But this is what the future brings. This is where we're looking at and where we need sufficient computing power. So with that, let me conclude with some of the major takeaways. And what we want to do is really build upon this picture from 5GAA with the V2X, vehicle to everything, to include also the satellite on this. I hope that comes. Yeah, here. So it's also vehicle to satellite, and does not just go to the car, it goes also to the infrastructure and to the other parts of the network. 5G NTN satellite connectivity is jointly pursued now in the framework of 5GAA and beyond by MNOs, automotive and space industry. Key to all this is really cross-industry co-innovation and co-creation. And that's why we're here, and that's why we enjoy talking to all of you, not just talking, but working with you. And for us, it's clear that also intelligent satellite payloads are the future and are necessary to integrate completely in this ecosystem. So I would end with what basically Olaf has said. Let's accelerate NTN. Thank you.